Hi, Weather and Forecasting Module 1, Part 3. Really quick, aerosols is a term that we use to account for any solid or liquid particles. Everything else that we've been talking about as far as particulate matter in the atmosphere, we were talking about the gas particles. Now these are solids and liquids. We fall under the category of aerosols. Some aerosols, if they fit well with precipitation, allows water droplets to stick to them. And if they are good at allowing water droplets to stick to them so that they can get larger and therefore heavier so that gravity can drag them back down to Earth, i.e. rain, we call them condensation nuclei. And so some aerosol particles are also condensation nuclei, but that is not true for every aerosol. So just because it's a solid or liquid particle in the atmosphere does not mean that it is a condensation nuclei. Condensation nuclei are often water droplets, so actual liquid already up there allows more liquid to stick to them. Some very specific leaf molds do it, and sea salt is very good as condensation nuclei as well. Taking a deep breath, we're now going to talk about the distribution of those air particles. So in our atmosphere, we can measure it based on its air density and air pressure. And air density directly relates to the amount of air particles present as I go up from the Earth's surface into the atmosphere to a point where I no longer will find particles of air density. This lovely chart basically shows that as I go up in the atmosphere, the particles that I find of things like nitrogens and oxygens become less dense or less packed together. So they become less frequently found and they are spread apart from one another. That means that as I go up in atmosphere, the density decreases. So as I increase in altitude, I decrease in density. Now, density of the air particles is just a measure of pressure. Pressure is basically telling me how many air particles are exerting their force down on me. And obviously, as I increase in atmosphere, I will have less particles above me and therefore less pressure. So air pressure decreases as I increase in altitude, which means that if I increase in altitude, both air density and air pressure decrease because the volume of air particles has decreased as I go up. It's pretty straightforward, but it's something that you do need to wrap your head around. And here is an example of that information, which brings us to the other way I can measure my atmosphere, which is through layers of atmosphere based on temperature profiling. So what is it doing as I increase in altitude? If I go up from the surface of the Earth, and as I increase in altitude through the surface of the Earth, I'm cooling off in temperature. That first layer that I go up in, where I'm cooling off, is known as the troposphere. I will eventually hit a point on that troposphere where I will pause. That pause is known as the tropopause, and that's because I'm no longer decreasing in temperature. It's not getting any colder anymore. It's not doing anything. It's staying exactly the same for a small amount of altitude. So I'll increase in height a little bit more, and then I'll hit a point where I have an unusually high amount of ozone. So going back into that one particle that we talked about, as well as a few other greenhouse gases like methane and nitrous oxide and water vapor. They're all present up there, but there's a high proportion of O3. And that means that it's very good at absorbing heat energy from things like sunlight and Earth's surface. And that layer actually increases in temperature as I increase in altitude. So I start to go up, and that layer is known as the stratosphere. So troposphere picture, stratosphere. Eventually, I will hit a point where I will have a smaller concentration of ozone, and that will make it so that it's no longer warming up, and I will pause again where I'll increase in height a little bit without any change in temperature. So I have my stratus pause, and then I will start to cool off again. This one's proportions go back to being very similar to our original amounts of percentages, where I have normal amounts of oxygen and nitrogen again, and not unusually high amounts of ozone. Most of the ozone is right here in the stratosphere. And that means I am decreasing temperature as I increase in altitude. Finally, I will hit a point where I will pause, but the pause is not nearly as wide, or the altitude is not as great on its not changing temperature as the pause in the stratus pause or the pause that's in the troposphere or the tropopause. So the tropopause and stratus pause have some good distances of altitude increase, where the mesopause going to the thermosphere is actually very, very thin. It's kind of just a small, minute amount of height in altitude. But then I will hit a point where I will hit the thermosphere. Now, the thermosphere does not have a lot of particles up there. There's not a lot. And they are very, very spread out. And anytime sunlight interacts with those particles, they are incredibly reactive. But the deal is they're so spread out that the opportunity to collide with those particles are very rare. And so the thermosphere is incredibly hot, but the particles are incredibly spread out. So the molecule that's vibrating way over here almost never gets to bump with the molecule that's vibrating way over here. So that warm temperature is kinetically separated in their activity on where they're vibrating. So I got one up here, one down here, and they're doing their activity, but they're not bumping into one another because they're so spread out when I get up to the thermosphere. So in review, the troposphere, which is the lowest level, the one that's closest to the Earth's surface, decreases in temperature as I increase in altitude. Then I tropopause till I hit high levels of ozone, and I will increase in temperature as I increase in altitude, and that is the stratosphere. Then I will run out of ozone, and I will pause, and that is my stratopause. Then I will go back to my 78% nitrogen, 21% oxygen, a lot less of my greenhouse gas, my variable gases, and that is my mesosphere, and I will decrease in temperature as I increase in altitude. And I will pause incredibly briefly in my mesopause, and then I will have very spread out particles, air particles, that are floating around up there. And they are highly, highly reactive with whatever sunlight collides with them. And they are incredibly warm at 1,500 degrees Celsius. And they are floating around, but they are so spread out, but they are increasing as I increase in altitude till I hit a point where gravity is still adhering some of those particles there, and they're just kind of flying off. And that's my exosphere, which is way out here. But they're not important to this class because these are the layers that are important for us to measure to determine. Now, almost all weather that we know of takes place down here in the troposphere. There is some that occurs in the stratosphere, or some conditions. And then we will talk about lenticular clouds and noctilucent clouds. And those are incredibly high altitude clouds that are taking place way up here, right around the mesopause. And so we will have some stuff that we'll talk about that's way up there. The next layers that I'm going to talk about, or the other way that I can divide up my atmosphere, is to talk about it as an ionosphere. So particles that are charged, electrically charged. Now, they're electrically charged because they're incomplete. So if I take oxygen and I'm missing a couple electrons, that oxygen that's missing a few electrons is lighter weight than the one that is nice and complete. And so all the nice complete particles, the ones that are heavier, have the proper amount of electrons, have greater density, and so they are all congregated at the surface of the Earth. On the other hand, if I'm missing some electrons, when density settled out in my atmosphere, I was a lighter particle. Therefore, I settled way up at the top in my mesosphere and thermospheric layers. So a lot of the particles that are way up in the mesosphere and way up in the thermosphere are missing electrons, which means that when anything enters our atmosphere, they are positively charged and looking for something to stick to. So when I get a little cosmic dust up there, those particles get very excited and they will stick and react to stuff that floats in. And that actually releases energy, also known as light energy, also known as the aurora borealis or the aurora australis, as we go through in our light energy. So on that note, there's some terminology that goes on to talk about Earth's origins and atmospheric material, and then just some terms like what is weather and pressure, what is mapping, what is station reading. Please take the time to just read through some of those terminologies and